Okay. Uh, Good afternoon, everyone. So, welcome to today's class. And today we are going to discuss a topic called primary structures. So far, what we have been discussing are called secondary structures. They're called secondary structures simply because they are the structures which form after a rock gets lithified. So, if you think in terms of sedimentary processes, uh, so there is a process of deposition, and after deposition, there is compaction and lithification, and by that process, sediment turns into a sedimentary rock. So, and similarly, if you think about igneous rocks as well, uh, first the lava or the magma actually flows to a particular place, and then after losing heat, it forms a sedimentary rock. So, the structures that are formed after the rock is lithified, the sediment actually becoming a rock, and you apply some sort of stress, it gets strained, be it in the ductile way or be it in the brittle way. It forms different sort of structures like fold, fault, joints, fractures, structures associated with ductile shear zone, goodinage, uh, all the things that we have discussed. But they are essentially after lithification, after rock formation, and they are called secondary structure, whatever we have discussed so far. But then there is also something called primary structures. Primary structures are the structures which are formed before lithification, before a rock is actually formed. So it could be during the volcanic flow or during the sedimentation process itself. So most of the structures that we are going to discuss, you have already seen them in your sedimentary geology classes, simply because the primary structures are formed by sedimentary processes. But as they are also called structures, so we will briefly discuss about them. Most of it you know already, maybe few of the things that you don't know, but most of it I assume that you have already learned during your sedimentology class. All right, so let me now present. So today I am going to present from a note which I will be circulating amongst you. And this particular note is a part of the Pathshala program of Earth Sciences. And I thought this particular note is very well written and very simple as well. So I recommend that after the class you read this note. I will send you via email this particular note, and also you will find uh, uh, the description of primary structures written in a very nice way in SKG's book. And it is there is a whole chapter called primary structures at the very beginning of the book. Okay. All right. So without any more introduction, let us get into the topic. So today what we are going to discuss are called primary structures or primary sedimentary structures. And they are broadly subdivided into three groups, as you can see here. The first group we call as predepositional structures or interbed structures. Pre-depositional simply because the sedimentation, the, these sort of structures uh, gets developed in a rock even before the sedimentation starts to form, even before the sedimentation process. Hence, they are called pre-depositional structures, and they are generally formed across two beds, two individual beds. They are called interbed structure. You will see when we discuss them. Then there are syn-depositional structures. Syn-depositional structures are the structures which form during sedimentation. So these pre-depositional structures are before sedimentation. Syn-depositional structures are uh, during sedimentation. And then post-depositional structures. These are the structures that form after deposition. And the post-depositional structures, if they are accompanied with deformation, they are called penny contemporaneous deformation structure. Please write this one down in your notebook. We call them as penny contemporaneous deformation structure, or they are called syn sedimentary deformation. Okay, so what does this mean? That even so, but remember, we are not talking about a deformation after lithification or after the rock forming process. We are talking about a deformation that is continuously happening while the sedimentation is happening or immediately after the sedimentation. Okay? So they are called penny contemporaneous deformation structure or primary deformation structures. And there are very characteristic features by which you can recognize them in the field, which we will discuss. Uh, the predepositional and syndepositional primary structures, I think you have already read a lot in your sedimentology class. But the third category, the post-depositional sedimentary structures, or the penny contemporaneous deformation structures, which are primarily resultant of deformation together with sedimentation. We will read them now in bit more details, although we will touch upon predepositional and syndepositional structures very briefly. But I also want you to remember two terminologies, okay? And if you please write this one down as well, will be very beneficial for you, because these are tricky questions that people ask in NET or GATE, or for in your GSI exam. So one we are talking about here as syndepositional deformation, okay, or post depositional deformation, pericontemporaneous deformation. Okay, so that means while sedimentation is happening, so the sedimentation is the primary process, there is a little bit of deformation happening. So syndepositional deformation or penny contemporaneous deformation, they are referring to the primary structures that we are going to discuss today. Now, there is another term also which is fairly confusing with this, which we call as syntectonic deposition. So syn sedimentary deformation and syntectonic sedimentation. Okay? I just take a PowerPoint and just write that down for you, because these two terms are often a bit confusing and people do make mistakes about understanding what people have asked. Write them down for you. So one is in sedimentary, sin sedimentary deformation, and they are any contemporaneous deformation structures, and that is included in the primary structures that we are going to discuss now. But a very similar term, but bit confusing, that is also used. So this is number one, which we are going to discuss now. The second one is called syntectonic deformation. Sorry, syntectonic sedimentation. So syntectonic sedimentation is primarily, the second one is primarily referred to, you remember we talked about the development of listric fault, and while the listric fault forms, we said that we develop growth strata, which is thicker closer to the fault and is thinner away from the fault. Yeah, so this is thicker closer to the fault, yeah, and thinner away from the fault. And this sedimentation is happening while this faulting event is going on, right? We discussed about this. So during this tectonism, the sedimentation is taking place, and this is we call as syntectonic sedimentation. But since sedimentary deformation is while the sedimentation is happening, so sedimentation here is the primary process, and while the sedimentation is happening, there is some sort of deformation as well. So be very careful what is asked in the question, whether it is sin sedimentary deformation, then your answer will be different, or it is syntectonic sedimentation, then your answer will be different. Okay. I hope I could make this point clear to you. Now, so let us look at these primary structures, and let us start with the predepositional structures. And some of the examples are, so these are even before the deposition actually happening: channels, Solmarks, Flute marks, and Gloobmarks. I think you already know about these structures, so I will show you some photographs, and you will be able to uh, understand them very quickly. Can someone just unmute or just write down if the sedimentary structures have already been discussed in your sedimentary geology class? These terms, all these terms are familiar to you, right? Can just someone write down yes or no? Can someone write down, please? No, sir. Yes, sir. Yes, sir. So I get yes, sir. Is the expected answer, Nirdesh? I'm surprised that you are saying no, sir. So if not, I will still take. I will take you through the structures, but I'm a bit surprised that you say no. But I will imagine that this has been covered already. All right, so let us start with predepositional structures: channel, soul marks, flute marks, and groove marks. Okay? So this is a beautiful picture of a channel. So you can see these are the rocks which are your bed rocks, and within which you can see the development of a beautiful channel. So the channel was supposedly flowing from perpendicular to the picture, right? It was flowing perpendicular to the picture, and this is the scoured mark of the channel itself. Okay? So this was the deepest point of the channel, and of course, then the channel sediment has actually filled this this structure, but you can very beautifully identify channel in your sedimentary rock strata. Okay? And these channels are particularly important because the sediments that you find in a channel bed are extremely porous and permeable. Okay, so they form beautiful hydrocarbon reservoirs as well. So, if you are a sedimentologist and working in the alluvial environment in an oil industry, then one of your primary job is to find out where in the subsurface these channels are, because the rock which is inside this channel is extremely porous and permeable and is a very good reservoir quality rock. Okay, so as we were talking about oil and gas industry, so one of the primary data source in the oil and gas industry, as you know, is seismic. And you can see this is a very beautiful seismic section. Yeah. And here also you can identify your channels. At least you can identify two channels, even more, maybe three channels. So this is one channel, a beautiful channel that has developed. Okay, there is a Thalweg here. Thalweg means the deepest point. You can identify another Thalweg here. And of course, you can see this is a beautiful channel that has developed within this bedrock, right? And you can, of course, also see that the character of the seismic signals are significantly different from its surrounding rocks, which actually helps you to identify this channel, or discriminate this channel from its surrounding. Now you can also observe another channel being developed here, and that channel is cut by another channel, and you can see the development of another channel here. Okay. So at least three channels you can identify from these seismic sections, and they are extremely important in oil and gas industry, as I said, because they are very good reservoir quality. They produce very good reservoir quality rock. Right now, what actually forms these sediments? These are the bars and the barrier bars. Sorry, the bars that are developed within the channel, that forms the channel sand. Okay, so the stacking of the bars within inside the channel, that is extremely well sorted, very good uh, roundness in the soil. Very good roundness in the sediment, in the sand, and hence it actually creates very good quality reservoir, form excellent porosity and hence permeability. Now the next type of mm, predepositional structure or erosional structure. So you can see that this channel is essentially an erosional structure, right? Why it is an erosional structure? Because this convex down geometry is only formed by the erosion of the channel. Okay? So it is an erosional structure. So the channel morphology itself is an erosional structure. Okay, and the erosion is done by the channel itself, by the river itself. Okay? Now, of course, the sediment which is being filled inside the channel is depositional, but the channel morphology itself is erosional, is predepositional, right? Now, similarly, we also observe things like scour marks, and scour marks are essentially formed. So this is a typical picture of the cast of a scour mark. What is cast of a scour mark? I will just explain to you. Say for example, this is a beautiful picture of a scour mark, the way it is being formed. So you can see, because of erosion, because of high current, there is this formation of a groove, or like a hollow space inside in the bed on this particular bed, and such beds, such hollow space can also be formed if you have an obstacle like this, and at the shadow zone of that obstacle, you can also form a beautiful scour mark, right? A negative morphology, depression, right? That is what you essentially form. Now, if there is sedimentation from the top of on the top of this particular uh, mark, what you will observe that and if you are lucky to actually get an exposure, so it's like this, that the so I created a scoured mark, right? And then, say for example, I have sedimentation. I have sedimentation from the top. Okay, so these are my. This is being filled up by by. This is being filled up by. What is happening? Is being filled up by sediment, right? Get my point. Is being filled up by sediment, and then if I just get the exposure of this particular rock, if I get the exposure of this particular rock only, okay, yeah, and if I just turn it upside down, it will appear as a, so wherever there was a negative impression, that will come as a positive relief on the rock which is residing on the upper side of that scour mark, right? So that is exactly what you are observing here in this particular picture. Okay. So these are the impression of the scours which have been developed on a rock which was immediately underneath. Right? And from this morphology of these beautiful scour marks which are being filled now, okay, and they are called soul marks, and the feeling of the impression of the scours on the upper side of the bed, on the overlying bed, are called soul marks. And by looking at the morphology of the soul marks, you can also define your paleocarbon direction. Okay, and I hope you have already studied these things in your sedimentology class, so I'm not getting into details. So this is a scour and fill structure, as you can see. So there was a scour, and this is now filled with younger sediments. Now, if I just being able to see this one, this will appear as a positive relief on the overlying bed. Similarly, groove marks or tool marks are developed by, say for example, I had a flat surface on which maybe I had some pebbles which actually, because of some current, has has traveled from this place to that place, so that will leave a scour or a groove on the top of this rock. And that is also an erosional or predepositional structure. That is what we call as tool marks. Okay. So flute casts are essentially similar to the soul marks, and they have a very typical asymmetrical elongated shape. Hence, we call them as as flute marks. And these are some beautiful pictures of, as you can see, of the groove marks. You know, from the groove marks also you can determine the direction of current. Okay. So now let us talk about some scene depositional structures, and you know about them, of course. The very primary structure that develops during sedimentation is your bedding. I mean, that's the very fundamental thing. And you know the law of superposition and the law of horizontality. So the sedimentary beddings are generally developed as horizontal layers, one above another. And if there is no deformation happening, then what you will observe that the oldest bed is essentially lying at the bottom, and the youngest bed actually lies at the top. So this is what we call law of superposition, and they generally get developed as horizontal beds. So that is what we call as law of horizontality. Okay. Of course, if the beds are extremely thinner, we call them as laminations. If it is considerably thick, say for example, as you can see here, if it is less than 10 millimeter thick, then we call them as laminated, and the laminated could be thickly laminated or thinly laminated. And if it is more than 10 millimeter thick, then we call them as bedded, or they're called beds. So they could be very thinly bedded, medium bedded, thickly bedded, or very thickly bedded if it is more than 1 meter of thickness. Right. So depending on, of course, the positional environments and the the slope at which the sedimentation is happening. Yeah, the slope, the hard slope on which sedimentation is happening also actually determines the shape of uh, the sedimentary layer. We can generally classify them as planar, wavy, or curved, and they could be parallel, non-parallel, and discontinuous. And there could be a series of permutations and combinations in between them: planar parallel, non-planar parallel, discontinuous, wavy, non-parallel, wavy, discontinuous, curved parallel, curved non-parallel, curved discontinuous. Sedimentology is so easy. It's very, very intuitive. I like it. And of course, flat beddings are often associated with parting lineations, and you know what parting lineations are. So I'm not going to describe them, but this is also a syndepositional primary structure. Okay. Then comes the topic of graded bedding, and you know graded beddings more than me, I hope, because your memory is fresh from your sedimentology class. So it can be either fining upward bedding or a coarsening upward bedding. The picture is not here. So fining upward bedding means the grain size essentially becomes from coarser to finer, from bottom to the top. So that is what we call as fining upward bedding. And if it is the reverse, then we call them as coarsening upward bedding. And essentially, that has very direct implication in terms of the depositional environment. So if I think of a fining upward bedding, that means, we are essentially coming from a proximal source to a distal source, right? So if my provenance becomes from um, proximal to distal, then I get more fine graded sediments. Say, for example, if we are thinking of a channel, at the very middle of a channel, we will find more coarse grain materials, and in the overlying deposit, of course, it becomes finer, and the sand even can transform into silt or shell because they are even more fine grained sediments, right? So it could be a graded bedding, and these graded bedding, the gradation essentially is very much related to the depositional environment. And you know about cross beddings, of course, and cross beddings are generally formed due to ripple or dune migrations. crossbeds are generally divided into two basic categories, like planar cross stratification and trough cross stratification. Yeah, and planar and trough cross stratification are generally, you can distinguish them if you are looking perpendicular to the flow direction. Then only you will be able to distinguish them. So in the perpendicular to the flow direction, you will see for planar cross stratification, the layers are generally parallel to each other. But in a trough cross stratification, of course, you see the development of beautiful troughs and filled troughs. Picture like is being depicted here. So that is my signature of a trough cross stratification. You already know where planar cross stratification and where trough cross stratification to develop. You know what is the foreset, what is the bottom set. Yeah, so I'm not repeating them. I'm sure you all have studied them before. So this is also a scene depositional primary structure. Okay, and these are some beautiful pictures of crossbeds, as you can see. Yeah, so top set, core set, you can identify them, and you can see that they are not asymptotic. Yeah, so you know what asymptotic crossbeddings do indicate, what sharply truncated crossbeddings do indicate. You are pretty much, I'm sure you are familiar with these things. Yes or no? Can anyone just write down? You are familiar with these things. What an asymptotic crossbeddings indicate? What a sharp crossbedding indicate? Anyone? Yes or no? Come on, write down, please. Only geology student, not ES and EES students. Sedimentology is your mandatory course, isn't it?
Sir, not for the environmental peoples.
It's not a mandatory course, really.
No,
But
sir.
but but
Yes, sir.
but, these things were also covered in your introductory earth sciences, isn't it? No.
Sir, not to that extent.
Okay, okay, very good. That's no problem. The note that I'm going to send it to you actually describes these things in detail. If you don't understand anything, the ES and ES people, you can get back to me and I will explain you again. Okay, all right. Okay, and of course, these are the ripple marks. As you can see, the ripple marks generally get developed because of either current or for wave, and generally we call them as current ripple and wave ripple. And due to the migration of these ripples, of course, you form cross stratifications. And if the ripples are of considerable height, we call them as dunes, right? These are my wave ripples, as you can see, as they are extremely symmetrical. And if they're not non-symmetrical, then we call them as current ripple, right? Symmetric ripples are generally related to wave ripples. And of course, they could be asymmetric. And as you can see, due to the flow of the sediment from lee to the stoss side of the material on the top of a ripple, you generally develop cross stratification. Okay, so there are so that if the cross stratifications are of a very smaller scale, we have like fissure bedding, lenticular bedding, and wavy bedding. So of course there is something called herringbone cross stratification. You know that so you have bidirectional currents in consecutive sets of uh, cross bedding, and then that actually refers to a tidal environment. I hope these things have been shown to you in your basic field trip. I'm not too sure. Generally, it should be shown, but if not, these. So you can see that the versions of these cross beddings are bidirectional. See, in one case, this closes this way, and in other case, this closes to the opposite direction. So that means you have bidirectional current. So, and bidirectional currents are generally very much indicative of a tidal environment. Okay, and these are called herringbone cross stratification. So these are all related to your thin sedimentary structure. There is also something called hammocky cross stratification. It's characterized by gently undulating low angle cross lamination and convex upward part. The hammock and the concave downward part, that is called swell. The spacing of hammock is several tens of centimeters to 1 meter or more in plan view, and they are dome shaped. Okay, they generally uh, are developed in a very low energy environment. Okay. So you know about debris flow deposits or gravity flow deposits. So there is extremely poorly sorted sand or mixture of sediments. So you have all sorts of sediments just dumped in an area that is a debris flow sediment, and that they are generally related to debris flow or granular flow that we have discussed before. You remember, and because of very high energy environment from the mountains, the debris generally come and dump itself at the mountain front. you know they are extremely dangerous, of course, if they happen today, like it happened, if you remember, in the Uttarakhand flood. So these debris flow are characterized by extremely poorly sorted uh, sediments. So you have sediments of different class size, and there is no gradation in them. Okay? It could be matrix supported, grain supported, and there is no significant sedimentary structure developed in them. Okay? I'm sure you know about turbidites as well. So turbidites, I'm not. It's a of course a very subject by itself. So I cannot essentially cover about turbidites. And turbidites are also similar slope deposits. So when you have a slope and a shelf, you know about them. When there is a transition from the ocean to the open sea, that is where the turbidites generally do develop. A very typical sequence that develops in a turbidite, we call them as Boma sequence. Okay, and they are also thin sedimentary structures. And of course, within the turbidite itself, you observe different thin sedimentary structures, right? Anyway, it's not the place to discuss about turbidites, and I'm sure that you have been taught about turbidites in your sedimentary class. If not, you read these notes, or you consult any sedimentary geology book. You can see a lot of information on turbidites. Okay, the important one, which we just talked about, at the penny-contemporaneous deformation structures. Penny-contemporaneous deformation structures are, as I said, while the sedimentation is happening, if there is a sudden shock or if there is some sort of deformation happening, you generally develop these sort of structures. Now, one of the important questions which are asked to a geologist: how to identify a penny-contemporaneous deformation structure? Okay, or distinguish a penny-contemporaneous deformation structure from a normal structure. So, say for example, I develop a fold during penny-contemporaneous deformation, and those sort of folds are called slump folds. We'll see what slump folds are in a while, and that is a product of penny-contemporaneous deformation. Now, what we observe generally in case of penny-contemporaneous deformation, is, say for example, I see a set of beds, okay, which are undeformed, and all on a sudden, some of the layers in between are folded. Okay, now maybe some layers are folded, and then again the rest of the layers are again unfolded, like horizontal or having the same dip as the uh, same regional dip. So what you observe that these folds, I don't know. You have been to this place called Seuni in Jabalpur when you were taken for the field trip, and I am sure you have been pointed out to these slum folds. You can see beautiful exposures of slum folds, okay? And you can see that you will, if you have noticed carefully, you should have observed that the underlying and the overlying beds are completely undeformed. But all on a sudden, there are some layers which are folded. Okay? So this is a typical signature of any contemporaneous deformation, that it is not penetrative. What do I mean by it is not penetrative? That it is only restricted to a single layer. It's not penetrative to the whole rock package. So if this would have been a product of secondary folding, we should have seen all these layers are actually folded. Okay, all these layers are folded, because if it is subjected to stress after the lithification has happened, you will not observe that a particular layer being subjected preferentially to be folded. Everything will be folded. Maybe the amplitude of the fold is different depending on the competence contrast or any other reason, but you the deformation should be all across your strata. It will not be just restricted to only one set of layers. So this is one of the ways to identify such many contemporaneous deformation structures. So what does that mean? So while this sedimentation was happening, for a very brief period, while this sediments were being deposited, they have still not been converted to rocks. Okay, they are still soft sediments, but they have maybe have been dewaterized a little bit, some thick mud sort of stuff, and then maybe there was an earthquake or there was something, when there was a little bit of stress on these rocks, and then they got folded. Okay, and which is preserved in the rock signature. But then that episode of deformation is very short lived. It came and it vanished, and then again these layers of sediments started to get deposited. So if you find such folded structures or deformed structures which are restricted within only a set of beds and which are not penetrative, you immediately know that this is your product of thin sedimentary deformation, right? They are not the product of secondary structures like the typical folds that we have been discussing. Is this clear? So what are the different types of thin sedimentary deformation structure do we observe? We see load cast, disc structure, ball and pillow structure, convolute lamination. This is very important. Convolute lamination, recumbent foreset, convolute bedding. Okay, and they are generally happening in a the nature of deformation is generally plastic. The sediments actually lag their shear strength. Okay? And then, of course, we see slumps and slides, and they are a product of thin sedimentary brittle deformation, and where the sediment has some sort of shear strength. Okay, as it is almost devoid of any cohesion, this has some sort of cohesion. Let us see some of those examples. Say, for example, this is what we call as a load cast. So you can see that so this rock is waterlogged mud bed, and this is a massive sand deposit, and they are still unlithified. Okay. Now, of course, there is a gravity imbalance. Okay, some heavier stuff is trying to sit on the top of a softer stuff. So, what will happen? Because if there are some pre-existing weaknesses, this massive sand body will try to actually sit inside. Will like to fall down inside, right? And then it will replace the mud, uh, the adjacent mud, which will kind of try to fill a space inside the sand. So this is what we call as a load cast, and then this is associated flame structure. So you can see here the beautiful development of, so this is this massive sand bed, which is actually forming a load cast inside this waterlogged mud. Perhaps this load cast, and maybe here there was a possibility of formation of a flame structure. You can see here the development of beautiful flame structures. You see here, these are load casts and the beautiful formation of flame structure. Just by looking at it, you can see, you can imagine that these have not formed after the lithification. This has actually formed while these rocks were still soft. And if you go to multiple number of fits, your eyes are so trained that you will be able very easily able to determine that these are load casts and these are penny contemporaneous deformation structures. These are not real folds. Yeah, some more if the load casts are of course having a disc like of shape, we call them as disc structures. You can see here the development of flame again. So these are the convolute laminations or convolute beddings. As you can see, and this is the example that I was giving. And these convolute laminations are very well exposed in Jabalpur. Can you tell me both the groups? Have you seen this in your field? Third year, 1% from third year, 1% from fourth year. Tell me if you have seen convolute laminations in your field. Yes or no? It was around close to the Seoni village, where your instructors must have shown you the MNB beds, top shell and then bottom carbonate. Have you seen these load casts or sorry, these slump structures? Prashasti, have you seen them? Just write down yes or no. What happens to the interaction of this class? Anyway, I imagine that you have seen them. But you can see here what is important to show that this convolute, this folding is extremely restricted only to this layer. There is no deformation here, okay, and there is neither in deformation here. So this is a very typical example of convolute lamination or a penny contemporaneous deformation. Of course, one of the things that you can see, by looking at these convolute laminations and their vergence, you can also determine the direction of current. It's not shear in these particular cases, like in the ductile shear zone. You remember that from the vergence of the associated asymmetric folding, we could actually determine the sense of shear. But here you can, by looking at the vergence of these convolute bedding, you can actually determine the direction of current. Recumbent forceps, similar stuff because of the flow of the current. One particular set of beds actually gets completely folded and forms like recumbent folds. But Again, this deformation is also not penetrative. They are extremely restricted to only one layer. Okay? It's a beautiful picture of a slump structure. So you can see here these beautiful foldings and disturbances and everything is only restricted within um, this layer, and rest of the layers are horizontally bedded. Okay, so this will immediately give you a hint that this is a very contemporaneous deformation. This is not a typically secondary structure, right? And while these beds were getting deposited, perhaps there was an earthquake or something, and all the rocks got um, completely shattered in a sense and formed this structure. And there are two things that you should see here. Sometimes it develops. So, like we have been showing, like a flame structure, it often develops a structure that looks like this. Okay, so this is sand. Shell, perhaps, and they are called injectites or seismites. So these are very typical of the signatures for paleo earthquakes. Okay? And if you can date this sand, you can actually date a paleoseismic event. Say, for example, I did a date this seismite, this sand, and I say that it got deposited maybe 100,000 years ago. So we can say at that date there was perhaps an earthquake in that area. These uh, beautiful elongated flame structures that you observe as a set of the penny-contemporaneous deformations are called seismites, and they're very typically used to date paleoseismic events. So that is penny-contemporaneous deformation. There are some other sedimentary structures which are called miscellaneous, like rain prints. You know, so these are like like you have seen, if there is a layer of sand on the top of it, if there are raindrops, they could be preserved as it is. Okay? And these rain prints, you can see if you go to Maihar, you can observe a lot of rain prints on rocks. Okay, so like say for example in the Precambrian time, those rocks come from the Precambrian time. You can observe the signature of rain at that time, right, on them. And finally, the desiccation cracks or the mud cracks. And I think I have talked about mud cracks more than once before. And they are uh, formed on a free surface. So if there is no stress, hence they are not uh, preferentially oriented, and the fractures form in all sorts of directions. And they form typical polygonal cracks. And then, of course, there are chemical sedimentary structures, which you can, I think, say, for example, stylolites, they form because of pressure solution. Okay. And you could have the layers of dolomite and calcite because some sort of oxygen fugacity did change, some magnesium influx did happen. And so, say, for example, we form geode structures as well, and they are like formed by vag feeling and beautiful growth of crystals, and you have seen them, I think, in the lab as well. How amethyst, you could see the formation of amethyst in them, or simple quartz. Mm, they typically also form during vag feeling as well. All right. And then, of course, there are stromatolites that can also form beautiful sedimentary, primary sedimentary structures, and they have different categories as well, which you can read from them. All right, then. So, these are the track marks or trail marks of paleo um, organisms. They are also um, kept as stress fossils on the top of a sedimentary rock, and they are also treated as sedimentary structures. Okay. Like barrows and, for example, barrows formed on a hard rock. If there is an organism, it forms a barrow inside which it actually lives. Yeah. Um, Sorry, barrows and boardings. If there is a soft sediment on which a particular, say, for example, a crab actually makes his house, makes its house and lives, and they are actually preserved. So they are called Boremarks, preserved as sedimentary structure. If the same is done on a hard rock, we call them as Boremarks. So Barrow is typically referred to when the sediment itself is softer, it's sediment still. But if it is a hard rock in which a particular organism makes his house, we call them as Boremarks. And they are also preserved as sedimentary structures or primaries. All right, then. I will, if you have any question on this. Or if not, then I will stop the lecture here. There is one thing that I want to inform you. Then this is regarding your lab. We just stop recording.